The learning intention of this lesson is to help you determine whether a molecule is polar or non-polar. It's good to get comfortable with this concept, as later in the course when we look at the Nature's Chemistry section, you will need to identify polar and non-polar components of soaps and emulsifiers. So these are the SQA learning outcomes that we're going to cover today. So the first one is a molecule is described as polar if it has a permanent dipole, and the second one is the spatial or 3D arrangement of polar covalent bonds can result in a molecule being polar. A polar molecule has a permanent slightly positive charge on one side and a permanent slightly negative charge on the other. To determine which side is positive and which side is negative, you will need to look at the electronegativity values in your data booklet. The first example we're going to use is this hydrogen chloride molecule. The electronegativity value for hydrogen is 2.2. The electronegativity value for chlorine is 3.0. Therefore, this chlorine atom will have a greater attraction for the bonded electrons in this polar covalent bond. So we're going to get a negative charge at the chlorine side and a positive charge at the hydrogen side. So we have a permanent dipole. Below this, we have a water molecule with two polar covalent bonds. The oxygen has a higher electronegativity value than hydrogen, so it will have a negative charge at the side with oxygen and a positive charge at the sides with the hydrogen. Jumping over to here, this molecule is called propanone, and it's got the C double bond O bond between it, called a carbonyl group. This is a polar bond in that the oxygen has a higher electronegativity value than carbon. So we're going to have a negative charge at the oxygen and a positive charge at the carbon. This molecule here, called acetonitrile, has got a triple bond in it, but we still need to look at the electronegativity values to determine the positive and negative end. Carbon has a higher electronegativity than hydrogen, so that means that there'll be a positive charge at this end. The nitrogen has a higher electronegativity value than carbon, so it's going to have a negative charge at this end. So you can see that each of these molecules has a positive charge at one side and a negative charge at the other, and you should be able to draw a line through each of these molecules to show a positive side and a negative side. Here are a couple of examples of non-polar molecules. To figure out if a molecule is non-polar or not, the first thing to do is look at the electronegativity values of the elements present in the molecule, which you can get from your data book. So let's start off with chlorine here as an example. This is a chlorine molecule. Because the atoms are identical, that means the electronegativity values are identical. So that means there's an equal attraction for the electrons in this covalent bond. There's no positive side or negative side, so this molecule we can say is non-polar. To the right here, we have a compound, phosphorus hydride. If you look at the electronegativities of the two elements in this compound, you can see that phosphorus has a value of 2.2 and hydrogen has a value of 2.2. So again, these are all non-polar bonds that the electrons are not drawn towards either atom. So overall, this molecule is non-polar. So to conclude, if in a molecule the electronegativities of all the atoms are identical, you can pretty much conclude that that molecule is non-polar overall. As well as considering the electronegativities of the elements in a molecule, the shape has to be considered as well, what we would call the spatial arrangement. If we look at hydrogen chloride, this permanent dipole generates a positive charge at this side and a negative charge at this side. This is the same with the water molecule as well. If we turn it this way, you can see that this more electronegative oxygen generates a negative charge at this side, leaving these positive hydrogens giving a positive charge at this side. Ammonia is another example of a polar molecule. Ammonia has a trigonal pyramidal structure. The two elements in ammonia are nitrogen and hydrogen. Nitrogen has a higher electronegativity value than hydrogen. If we look at the 3D structure of ammonia, and we look at the partial negative charges in the nitrogen and the partial positive charges in the hydrogen, we can see that this is a polar molecule. This molecule, called trichloromethane, is also a polar molecule because it has a positively charged hydrogen and 3 negatively charged chlorines at the bottom end. And you can see, if you look in 3D, this is your positive side and this is your negative side with electronegative chlorines. Even if I rotate it, it still has a kind of non-symmetrical shape. This molecule is called carbon tetrachloride. If we look at the electronegativities of the two elements in the molecule, we'll see that chlorine has a value of 3 and carbon has a value of 2.5. This means the chlorines will have a partial negative charge around their atoms, while the carbon atom has a partial positive charge. So this means that we have polar covalent bonds within the molecule. Does the presence of polar covalent bonds mean that the molecule is polar? Well, if I draw a negative charge on each of these chlorine atoms, this might make it more apparent what's happening here. Whatever direction I approach the carbon tetrachloride, I'm always encountering a negative charge. Every side, if you like, is negative. There's not a positive side or a negative side. So because the molecule is symmetrical, we say that we have a non-polar molecule. We often say that the polar covalent bonds cancel each other out. So it's possible to have a non-polar molecule with polar covalent bonds if it's symmetrical in shape, like this. Another example of a non-polar molecule that has polar covalent bonds is carbon dioxide. Carbon dioxide forms a linear molecule like this. If we look at the electronegativities of the elements in carbon dioxide, carbon has an electronegativity value of 2.5 and oxygen has an electronegativity value of 3.5. This gives this side a negative charge and this side a negative charge, giving a delta positive above the carbon. Now, one thing to note, that like carbon tetrachloride, CO2 is a symmetrical molecule. It doesn't matter whether I approach from this side or this side, there's a negative charge. So if I look at this in this way, you can see it's negative at this side and negative at this side. So because this is a symmetrical molecule, it doesn't have a positive end and a negative end. This is a non-polar molecule overall. So it's got polar covalent bonds, but the overall molecule is non-polar. One more thing to note as well, that if you have a hydrocarbon molecule, it will be non-polar as well because these are symmetrical molecules. So we have this tetrahedral shape here, where every atom is the same. Whatever way I approach, I'm encountering a hydrogen atom, which in this case will be slightly positive. The same goes with this ethene molecule. This is symmetrical in shape, and whatever direction I approach this, I'm encountering a hydrogen atom with a positive charge as well. So hydrocarbon molecules are also non-polar in nature too. To recap, the spatial arrangement of polar covalent bonds can result in a molecule being polar. Taking this molecule as an example, the chlorines will give a negative charge at the lower end of the molecule, and the hydrogen will have a partial positive charge at the top of this non-symmetrical molecule. So we have a permanent dipole with a positive end and a negative end, and this is because the molecule is not symmetric. You can see that if we draw a line through it, one side is different from the other. We have a positive charge at this end and a negative charge at this end. However, if the molecule is symmetrical, it may be non-polar overall, even if polar covalent bonds are present in the molecule. So to take carbon tetrachloride as an example, we have polar covalent bonds here between the carbon and the chlorine. This will generate partial negative charges in the chlorine atoms in this molecule. However, we don't have an overall permanent dipole in the molecule because it's symmetrical. So even if we did a line of symmetry through the molecule, we don't have a positive side and a negative side. every side you approach this molecule from, it's going to give you a negative charge. So we describe this molecule as being non-polar, even though it's got polar covalent bonds. The same goes for carbon dioxide. We can draw a line of symmetry through this, and we can see that whatever side you approach this molecule is going to have a negative charge. So these are the two shapes you should probably try and remember in terms of remembering what type of molecules are non-polar if they have polar covalent bonds. Hydrocarbon molecules are non-polar too. Although within the molecule there is a slight difference in electronegativity values between carbon and hydrogen, it's quite low, so it's not particularly polar. The molecules overall have a symmetrical shape. So if we look at butane, for instance, we can draw a line of symmetry. The same goes for ethene, cyclohexane, and methane. So to summarize, you can have non-polar molecules with polar covalent bonds. I suggest you remember these shapes and know some examples of compounds that have these shapes. So taking this one for instance, if you have an atom such as carbon or silicon which forms 4 covalent bonds and it is covalently bonded to 4 identical atoms, this will be symmetrical and be nonpolar. Carbon dioxide is another example, as well as any hydrocarbon molecule such as hexane. Here is an exam past paper question for you to try. So pause the video and have a go at it to see if you get the correct answer. So to tackle these kind of questions, there's 2 things to consider to determine whether a molecule is polar or not: the electronegativities of the elements present and the shape of the molecule. If you look at the electronegativities of the elements present, there is a difference between the two for each of the molecules, so they're all going to have polar covalent bonds. So now we need to look at the shape of the molecules. If we look at carbon dioxide first and draw the shape of it like this, you can see that it has a symmetrical shape, so it is going to be nonpolar. If we look at carbon tetrachloride, it too has a symmetrical shape, so it is nonpolar. And if we look at methane, it also has a symmetrical shape and it's a hydrocarbon, so it is going to be nonpolar too. If we look at the shape of an ammonia molecule, you can see that the nitrogen is more electronegative than these 3 hydrogens, so it's going to be a partial negative charge on this nitrogen atom with a partial positive charge on these 3 hydrogen atoms. So we're going to have a negative charge at this end and a positive charge in this end. So overall we have a polar molecule. So here's another question for you to try. So pause the video and have a go and see if you get the correct answer. So the question is asking which of the following compound is made up of non-polar molecules. So it's either going to have atoms with the same electronegativity or it's going to be symmetrical. And the answer for this one is going to be carbon tetrachloride, because it is the only molecule out of these 3 that is symmetrical. They all have polar covalent bonds, but the carbon tetrachloride is the only one that is symmetrical. You can see whatever direction we approach this from, it's going to have a negative charge. Here is another exam question requiring a written response this time. So have a go at it, pause it, and then see if you've got it right. So basically this question is asking you which of these 2 molecules is more polar. To determine which one's more polar, we need to look at the shapes of the molecules. In this case, they're both the same. So we need to look at the electronegativities of the elements present in the molecule. If we look in the data book and get down the electronegativities of the elements and put them down, you can see if we look at trichloramine, the electronegativities of nitrogen and chlorine are identical. So therefore we've got non-polar bonds present in this molecule, so we can say that this molecule is non-polar. In ammonia, there's a difference in electronegativities between the nitrogen and the hydrogen. So therefore we have polar covalent bonds present in this molecule, so we can say that ammonia is a polar molecule. So you would get 1 mark for mentioning that ammonia is polar and trichloramine is non-polar, and another mark for an explanation in terms of polarity and electronegativity. And it's a good idea in exam questions to write down the electronegativities next to each atom, as this will help you figure out what the correct answer is as well. Okay, so this is the final question. Have a go, pause the video and see if you're correct. So the first thing we need to do here is draw the full structural formula for tetrafluoroethene. And even though the molecule may be unfamiliar, we have enough clues within the name to tell us what the molecule is. The eth part tells me there's 2 carbons, and the ene part tells us there's a double bond. So we can put down a carbon-to-carbon double bond. And the tetrafluoro part of the name tells us that there are 4 fluorines attached to the 2 carbons. To see whether there are polar bonds or not, we need to look at the data book and put down the electronegativities, and you can see there are polar carbon to fluorine bonds present in the molecules, giving polar CF bonds. So we know that the answer is either going to be A or B. We definitely have polar covalent bonds present in the molecule. Is it a polar molecule? Well, we need to see whether it's symmetrical or not. And you can see if I draw a line down here, we have an axis of symmetry going from top to bottom. So this is a symmetrical molecule. So the molecule is symmetrical, so we say it's non-polar overall. So the correct answer then is B. We have polar bonds, but the molecule is non-polar. So the correct answer for this will be B.